The busiest maritime route on the planet. 35 kilometers of icy, unforgiving waters separate two continents, and for more than 200 years, generation after generation of engineers, politicians and dreamers have dedicated themselves to one idea, uniting them, not with ships, not with bridges, but with a tunnel beneath the seabed. The first formal plan was presented in 1802. Napoleon Bonaparte still ruled France. Horses were the primary means of transportation. Streets were lit by oil lamps. And even so, a French engineer named Albert Mathieu drew up plans for a tunnel beneath the English Channel, complete with ventilation shafts rising above the waves. It was a completely impossible idea for the time, but it planted a seed. Throughout the 19th century, the dream resurfaced repeatedly. In 1880, the British actually began excavating a test tunnel. They advanced nearly 2 kilometers. Then the British government ordered work to stop. Fear of a French invasion outweighed any promise of progress. For now, the sea still won. Attempts followed for decades. Studies, proposals, endless parliamentary debates, 4 false starts. Each time, politics, fear or money stood between ambition and completion. But at the end of the 20th century, something changed. Post-war Europe had spent decades building bridges, not just of steel, but economic, political and cultural ones. The idea of physically connecting the United Kingdom and France was no longer a romantic fantasy. It was a strategic necessity. In 1984, Prime Minister Margaret Thatcher and President François Mitterrand sat face to face and agreed to do what no leader had ever managed before. Actually build it, 2 nations, an extraordinary risk and a project that would change the world. They were not merely building a tunnel. They were uniting 2 economies, 2 cultures that had eyed each other with suspicion for centuries, through an underground corridor of steel, concrete and human willpower. The final design was bold in its simplicity. 3 parallel tunnels beneath the sea, 2 main rail tunnels, 1 in each direction, and between them a central service tunnel. That 3rd tunnel was the heart of the system. The emergency access route, the maintenance artery, the lifeline in the event of catastrophe. On the French side, the small village of Sangatte, near Calais, became the epicenter of the French operation. A quiet community of fishermen and farmers that suddenly found itself surrounded by cranes, engineers and thousands of workers. In England, a site was chosen south of Folkestone, at the foot of the legendary White Cliffs of Dover, the same cliffs Winston Churchill had gazed upon during the Second World War as a symbol of British resilience. Now they would be the departure point for the largest civil engineering project Europe had ever seen. Before moving a single gram of earth, the project's greatest problem, geology, had to be solved. The bed of the English Channel is not uniform terrain. It is layered with different types of rock, each with distinct properties and its own hazards. Engineers spent years drilling into the seabed, extracting samples, analyzing every centimeter of the proposed route. And they found what they were looking for. A layer of chalk marl, a rock with a particular composition, hard but with one crucial characteristic. It was almost completely impermeable. The problem was its thickness, only 20 meters, and the tunnel had to be built 75 meters below sea level. If the tunnel boring machines deviated even a few meters upward, they would breach porous rock. Channel water would flood in with devastating force, a catastrophic and unstoppable inundation. If they deviated downward, soft clay would trap the machines, swallowing them whole. The margin for error was practically zero, and they needed to maintain that precision for 39 kilometers. Even before excavation began, they had to solve another colossal problem: how to position the tunnel boring machines. On the English side, engineers were confronted with a vertical cliff face more than 100 meters high. There was no way to lower a boring machine down that rock wall. The solution was drastic. They dynamited 250,000 cubic meters of rock, 250,000 cubic meters. They blew part of the cliffs of Dover away to create a flat platform from which to launch the machines. All that rock and debris did not disappear. The material was deposited into the sea, creating a new 36-hectare coastal platform. They literally manufactured a new piece of Great Britain. The English Channel was pushed back by several meters. On the French side, the challenge was different but equally monumental. The terrain was lower, closer to sea level. The solution was to excavate downward, a vast circular shaft 60 meters deep, from which the tunnel boring machines would be launched directly into the earth. The pressure at that depth was already immense, and the tunnel boring machines, the true protagonists of this story, had not yet even begun operating. They were not purchased from a catalogue. They were designed and manufactured specifically for this project, tailored to the exact geological conditions of each section of the tunnel. 11 machines in total. Each one was a self-sufficient underground factory, a miniature city that advanced slowly through the rock, building the tunnel as it moved. The front cutting head alone weighed 600 tons, a giant disc covered in tungsten carbide teeth that rotated incessantly, crushing rock with brute force. Behind the head, hydraulic arms gathered the rock fragments and conveyed them back along a conveyor belt. And as the machine advanced, other arms installed the prefabricated tunnel lining segments, rings of reinforced concrete produced in specialist factories, transported to the working face and positioned with millimeter precision. These segments were watertight. They were the only thing that would separate the workers from millions of tons of water above their heads. The British side mobilized 6 machines, 3 for the land tunnels connecting the Dover portal to the underwater section, and 3 for the underwater section itself, the most critical and dangerous. The French machines were technically different. Closed-face boring machines designed to operate under compressed air pressure because the ground on the French side was wetter, looser, and more treacherous. Mechanical pressure alone was not enough to hold back the water. The working environment itself had to be pressurized. Imagine working in a confined space without adequate ventilation at temperatures that could exceed 50 degrees C under high atmospheric pressure, with the weight of the English Channel pressing down on you. It was a pressure cooker kilometers from sunlight. The Central Service Tunnel took the lead. Smaller and easier to manage, it would be the exploratory tunnel that paved the way for the main rail tunnels. Every meter was a gamble. Engineers and technicians constantly monitored water infiltration, the first sign that something was wrong. Any leak, however small, had to be located immediately and injected with cement grout before it became something worse. Large-scale flooding was a constant threat. At several points during the project, water broke in with enough force to threaten to trap entire teams inside the boring machines. And on top of all this, there was the pressure of the deadline. The private investors financing the project, because yes, this was one of the first major infrastructure projects financed entirely by private capital, demanded results. Every day of delay cost a fortune. To maintain the absolute precision demanded by the chalk-marl layer, engineers developed systems that would be considered sophisticated even by today's standards. A laser beam projected from the rear maintained the visual reference of the correct path, but the primary guide was a high-precision gyroscope, an electronic compass capable of detecting and recording every minute deviation from the steering axis. The boring machine operator read the gyroscope data in real time and adjusted the machine's direction as if driving a 1,000-ton lorry through a 20-meter-wide tunnel. Kilometer after kilometer, week after week, month after month. The debris problem was monumental. 7.5 million cubic meters of crushed rock. It all had to go somewhere. The spoil from the French side was transported and deposited in designated areas on land. The spoil from the English side took a different route. It was dumped directly into the sea alongside the Dover portal, eventually forming a new 36-hectare coastal platform, a new artificial promontory. When you do not know where to put the earth, you build an island. Meanwhile, the main rail tunnels advanced more rapidly, with larger and more powerful machines. The rate of progress under ideal conditions reached 75 meters per day, but ideal conditions were the exception, not the rule. After 3 years of continuous work, the moment of truth was approaching. The excavation faces of the service tunnel, one coming from England, the other from France, were just meters apart. 39 kilometers of rock, bored from 2 opposite ends, guided only by gyroscopes and lasers, were about to meet. 2 separate worlds, boring blindly toward a common point. The accumulated error could be fatal. If the calculations were wrong, if the gyroscopes had drifted even slightly, both faces would overshoot each other. The tunnel would not connect, it would have to be demolished and the process begun again. On the 1st of December 1990, the first pilot bore was drilled, a narrow tube that pushed through the last meters of rock. And through that hole, English and French workers saw each other for the first time. The handshake that went around the world. The final alignment error, less than half a meter across 39 kilometers at 75 meters depth. A precision that defies imagination. The chalk marl had held. The risk had been worth it, but the celebration was brief. The tunnel boring machines had finished their work, but now they had to be dealt with. The French machines were dismantled piece by piece inside the tunnel and extracted to the surface. A titanic feat of reverse engineering. The British machines were simply too large. There was no way to turn them around. There was no space to dismantle them without blocking the tunnel for months. The decision was taken coldly. Seal them, shift them slightly off the tunnel alignment, bury them in the rock and seal the entrance. 6 machines, each weighing 1,000 tons, lie today beneath the English Channel, entombed forever, sacrificed to save the schedule. It is possibly the most extraordinary industrial burial in history. With the tunnels excavated, the fit-out phase began. The tunnels needed air, light, and safety. Enormous industrial fans were installed at both ends, capable of completely renewing the atmosphere inside the tunnels within seconds. A ventilation failure is not merely an inconvenience, it is a catastrophe. The 25,000-volt power cables for the trains were installed with surgical precision. Touching that line while it is operational is an irreversible mistake. The rails were welded using a special technique, without conventional joints, to create a perfectly smooth surface capable of supporting trains traveling at 160 km/h beneath the seabed. And then security, the greatest challenge of all. The greatest fear in an underwater tunnel is not water, it is fire. A fire in a confined space, with no direct exit to the outside, can be fatal within minutes. The solution was the 3-tube design. Every 375 meters, a cross-passage connects the rail tunnels to the central service tunnel. In an emergency, the central tunnel becomes the refuge. A complete fire suppression system runs the full length of all 3 tunnels. Sensors, sprinklers, alarms, and redundant emergency lighting capable of functioning even if all primary systems fail. The first trains ran in 1994, but the project faced severe financial difficulties. The originally estimated cost was $4.7 billion. The final cost was $55 billion, double. Private investors were furious, and the construction companies were nearly bankrupt. The company responsible for operating the tunnel, Eurotunnel, would take decades to recover from the debt. The engineering had been a miracle. The finances had been a disaster, but the tunnel worked. The terminals at Folkestone and Coquelles were architectural marvels in their own right. Enormous logistical centers designed to process thousands of vehicles per day. Cars, lorries and coaches loaded onto special wagons and transported beneath the sea in 35 minutes on a high-speed underground crossing. Then came the real test. In November 1996, 2 years after opening, a fire broke out in a freight wagon loaded with lorries. The tires and cargo burned intensely. The fire suppression systems were immediately activated. Staff evacuated passengers into the central service tunnel. Everyone survived. The three-tunnel design proved its functionality under the worst possible circumstances. The service tunnel proved to be the lifeline its creators had promised. Today, the Channel Tunnel carries more than 10 million passengers per year. The Eurostar connects London to Paris in just over 2 hours, without airport security queues, weather cancellations, or the stress of flying. It is the culmination of 200 years of dreaming. 4 failed attempts, 7 years of construction, 14,000 workers, 11 deaths that deserve to be remembered, and an investment that nearly drove its creators into bankruptcy. The physical connection is permanent, an unbreakable bond of steel and limestone. They said the sea was a wall. The Channel Tunnel proved that human ingenuity can overcome any natural barrier. One of the greatest feats of collaborative engineering in the history of humanity, not only for what they built, but for how they built it. 2 rival nations with different languages, cultures, and technical systems working together toward a common goal. The next impossible challenge is already underway. This is the true connection. Do not miss what is coming.